Okay, today I've got my terrain grid displacement, vertex displacement project, and it's a bit of a disappointment. I did a lot of work to reinvent the wheel here because I made some sort of incorrect assumptions about it. I decided, oh, I should let it take in any random set of points and generate a surface out of that. So I did that. So I get the Delaunay triangulation of all the points, and then I make a grid that is the bounding box for those points. Like we can see here, this little corner is outside of the convex hull of all of those points, so it's just flat. I make a bounding box grid, and then for each of the points on the grid, I just sample the Delaunay triangulation and linear or barocentrically interpolate the height coordinate for each point in the grid, which not really thinking about the fact that just barocentrically interpolating the height position of each of these is the same thing as just drawing the triangle, except worse because now the edges are not smooth, which is just objectively, I think, worse. I guess that's subjectively, but it's just worse than just drawing the triangles that you get from the Delaunay triangulation. My thought was, now obviously, like looking back, it's completely inaccurate, but my thought was to get something like a smooth interpolation, sort of like a NURBS or a Bezier surface from these, which finding out now is fine, but obviously that's not what I wrote. But I can show you the code because it is kind of an interesting little algorithm I cooked up to do next to nothing. So I'll show that. And then I also did just do a really simple terrain thing where I just take a grid of data and then I turn it into a height map. But it's less work than the other one. So what I'm doing is getting this mesh. So I take in, this is just arbitrary data. It doesn't have to be grid aligned or anything. And then I make sure that it's sorted top to bottom, left to right. So basically in a linear vector of positions. So it should go X first and then Y, just like if you're stacking a 2D array into a one-dimensional vector. Okay, so I take that, and then you know what? I missed something. Because the first thing I have to do for the interpolated one is I map it to a grid. So I go to this. So first thing I do is the Delaunay triangulation library that I use. You need to do a data transformation first. So I do that, and then I get the minimum and maximums of the input data. That way I can get the bounding box. And then I do what is the step size going to be, like how far apart is each point going to be. And then right here, I am getting the X and Y coordinates for that grid spot, and then offsetting it so that it's starts at the minimum Y and minimum X. And then I do a check that says, is the point in the convex hull? So you just go through all of the edges in the convex hull, edge AB, and then you make sure that the dot product, the perpendicular 2D dot product of A to B is dotted with A to the point that you're checking. Should be less than -1 or less than 0. And the reason I do that is because I did my y's as y starts at the top left and goes down. So to do a counterclockwise turn, normally it would be above 0 for a counterclockwise turn, but because I'm essentially doing a vertical mirror, it's really a clockwise turn that we need to do. So that, and then once we do that, that checks. We get what are the vertices of the input data triangle that from the Delaunay triangulation that contain this gridded point. So I just loop through all of the triangles that the Delaunay triangulation has, and I check and see if it's in the triangle, which are the points on the same side of the line. This is, I think there's several ways that you can do this. I could have done it the same way as this, I believe. But I didn't. So essentially, the line A to B and the line A to the point needs to both be the same turn, directional turn, away from A to C. And then same thing for all the other three. So it's the one edge to one edge, and then the direction to the point dotted with the opposite edge. So that is what we do next. And if the point's in the triangle, then we return the data points for each A, B, and C index. So then we go back here, and then we do the barycentric interpolation. And this is a sanity check because this can, if any of these are negative, it says that we're outside of the triangle. I could have just done the barycentric interpolation for all of the triangles and seen which one this was positive for. All three are positive for, but I personally I didn't do any testing on it, but I am guessing that the point is in the triangle function is probably going to be quicker, just because it's just a few dot products rather than the whole barycentric interpolation, which is a lot of more math, though I'm sure the compiler probably works a lot of that out. The real reason is because I'd already had a function written. I didn't realize barycentric interpolation would do that, and I'd already written this point is in triangle function. So by the time I got to barycentric interpolation, I'd already written this, so it didn't really make sense to rewrite the whole outside algorithm to use this as both the check, whether it's in there, whether the point is inside of the triangle, and also doing the interpolation. So do the barycentric interpolation, and then using that, we set the y coordinate, so the data coordinate for that position. And then we do that for every point on the grid. Okay, so then once we've done that, this is the only thing that's different between the interpolated one and the non-interpolated one. So then this is the same for everything. So it just takes in a collection of points, and they don't have to be sorted at all, because we sort them here. And then we turn them all into the vertices for the model, and then we create a grid using the same sort of grid strategy that we did for the heat map grid. And then because we're not just having a flat surface, we need to deal with the normals. So I get all the normals for each face. So I just go through for every 3 chunks of the vertices. No, for every 3 chunks of the indices. So that's 1 triangle. I turn that into a element of a hash map so that you can just directly look up. I have these 3 vertices, A, B, C, and it's really indices. So I have like 3 unsigned 32-bit integers, and I can get the vector, the normal vector for that face. So we do that, and then we get the vertex normals. So for each of the vertices, we do summation and then normalization of the surrounding faces normals. And we're only doing the 6 faces surrounding because I didn't do I just do the like this. So for 5 gets this one, but it doesn't get the 5 vertex does not get zeros. 0, 4, 1. It doesn't get that face as normal included. So it's not ideal. Okay. So for each of those, we just see if there should be a face there. And then if there's supposed to be a face there, we get the normal for the face. And then once we have all of the faces, we normalize them. And that's similar, or I guess that's equivalent to taking the average. And because if we don't have a face, like if this is false, we just add 0, so it does nothing. So we don't have to check what combination of these we actually have to make this part right here work. And then we just turn it into a list of those vertex normals. And then once we have those, we modify all of the vertices to have the correct normals. And then we just send everything over to the graphics card. So let me go ahead and change this back to the other this one isn't doing any interpolation for the data. Every data point is a vertex in the actual mesh. But we actually got to use the same generate terrain mesh and generate materials for them. So, which is pretty nice. Okay, so once again, we still have light flowing around. So this is just a Berlin noise mesh. And it's clamped from 0 to 1, so where it goes over 1, it just is flat. So yeah, I mean, this is the simpler way of doing it. If I'm gonna need to continue to work on this for my thesis project, so I'm going to do either Bezier surfaces or NURBS or something to make surfaces with control points, because that's really what I was going for in practice with the interpolated meshes. I just wasn't thinking about it in those terms, so kind of went down the wrong path, but I guess that's how projects like these go sometimes. So this is a 512 by 512 mesh. So 512 data points, 512 vertices squared. So once again, you can see a little bit of like lighting weirdness because of the way I'm calculating the normals. That is also something I would need to change. I would just need to change how the actual how the grid is laid out so that I could have 8 vertices surrounding each vertex instead of 4, or instead of 6, or sorry, 8 faces surrounding every vertex instead of 6. Anyways, that's all I have.